All right, in this video, we are going to take a look at this problem. We want to find the intervals on which f is increasing and decreasing. And our function is f of x equals x plus 4 times e to the 2x minus 1. So the first thing we want to do is to find the domain of this function. And looking at it, we have x plus 4, which is a linear function, polynomial, and 2x minus 1, which is also a polynomial. And then the 2x minus 1 has been composed with e to the x, right? The 2x minus 1 function has been plugged into e to the x, and e to the x also has domain all real numbers. So since this function is made up of pieces which have domain all real numbers, and we're not doing division, it's just multiplication and composition, then this function will have domain all real numbers as well. All right, next up, we need to take the derivative. To take the derivative of this function, we are going to use the product rule. We have this function x plus 4, and it is being multiplied times e to the 2x minus 1. Okay, so taking the derivative of this, the derivative of x plus 4 is just 1, and then the product rule says just rewrite the other function. Then the product rule says put a plus. And then in the next go round, the function that we took the derivative of the first time, which is x plus 4, leave it alone, and then multiply by the derivative of the function that we left alone the first time. Well, that is a chain rule problem, e to the 2x minus 1, finding its derivative, right? That function has an inside part of 2x minus 1 and an outside part of e to the x. In other words, this function e to the 2x minus 1 was formed by taking the function 2x minus 1 and plugging it into the e to the x function, or it's the composition, right, of those two functions. So we would use the chain rule. The chain rule says you need to take the derivative of the outside part, which the derivative of e to the x is just e to the x, then plug the inside into the derivative of the outside part, right, which again is called composition, right, of those two functions. So take this 2x minus 1 and then plug it into the e to the x, plug it in for x. And then the last step of the chain rule is to multiply by the derivative of the inside part. Well, the derivative of 2x minus 1 is just 2. Okay, so the last step is to multiply all of this by 2. All right, so we're done taking the derivative. We do need to simplify this as much as possible. In order to simplify this as much as possible, the best way is to factor out any common factors that you have here. And here the only common factor is this e to the 2x minus 1. So I'm going to factor it out. All right, when I factor e to the 2x minus 1 out of this first term, I'm just left with this 1 right here, and then this plus. And then out of the second term, this right here, I'm left with 2 times x plus 4, like that. So factor out whatever you can out of those two terms that you have there, and then doing some more simplification, I get e to the 2x minus 1. Here I can distribute that 2x through the parentheses. And then combine the like terms. I have this 1 and this 8. So, and I'm going to write that term out in front. So I get 2x plus 9, and then e to the 2x minus 1. So there is the derivative simplified as much as possible. All right, and so the next step is to solve the inequality f prime of x greater than 0. So take the derivative, right, 2x plus 9 times e to the 2x minus 1, set it greater than 0, and solve that out. So that is a nonlinear inequality. So what you want to do first is to set it equal to 0 and solve. Okay. To solve this equation involving this exponential function, right? You want to get this factored as much as you can, which we already did all that work back up here. So since this side is factored, the left side is factored as much as possible, and I have 0 over here, right? That means I'm multiplying these two expressions, 2x plus 9 and e to the 2x minus 1, and I get 0. So if I multiply two things, two numbers, and I get 0, that means one or the other or both, right, had to be equal to 0. So take each of these factors and set them equal to 0. And now solve those. All right, this equation here, e to the 2x minus 1 equals 0, that has no solution. The reason why it has no solution is that if you plug any number into the e to the x function, you will get a positive number. You will never get 0, right? So there is no number that I can plug in for x, right? Whatever number I get up here, e to that number will be positive. So it just has no solution. And then solving 2x plus 9 equals 0, you'll wind up with x equals negative 9 halves on that one. Okay. All right, so negative 9 halves is a possible critical number, right? We need to take those possible critical numbers, all of them, and put them on a number line that represents the domain of the derivative. Excuse me. Oops. All right. So here is my number line representing the domain of the derivative. The domain of the derivative, for exactly the same reasons that we talked about up here when we were finding the domain of f, it is all real numbers, right? And then somewhere in there will be negative 9 halves. So all your real number solutions from this need to go on the number line. And those are your possible critical numbers. We only have one possible critical number here. That's negative 9 halves. At this point, it is a good time to check those possible critical numbers to see if they are actually critical numbers. Right? Remember, they must be in the domain of the original function f. The original function f has domain all real numbers, so that means that negative 9 halves is a critical number. All right, so that's going to be important later on when we look for local maxes and local mins. Okay, so our possible critical numbers divide up the domain of f prime. In this case, there's only two pieces, the piece to the left and the piece to the right. All right, and what you want to do on each of those pieces is to pick a test number. So here to the right of negative 9 halves, I'm going to pick 0 as my test number. And then over here to the left, negative 9 halves is about minus 4.5. So I'm going to pick minus 5 over here. All right, and I'm going to take those test numbers and I am going to plug them into this inequality right here. Okay. 2x minus 9. Oops, it's actually plus 9. Right? Yep. E to the 2x minus 1 greater than 0. All right, so I'm going to plug them into this inequality right here and to see what I get. Okay. Okay. And the reason why I'm doing that, right, is remember, it's all or nothing on each one of these pieces, right? So either every number is a solution to this or no number is a solution to this. All right, so when I plug 0 in, I get 2 times 0 plus 9 e to the 2 times 0 minus 1 greater than 0. Okay. All right, so evaluating that, 2 times 0 plus 9 gives me a 9. And then 2 times 0 is 0 minus 1. I get e to the minus 1 greater than 0. Okay. So if you have a calculator, you can just plug that into the calculator. I don't have a calculator here right with me. But I do know that this is true. Remember, I said e to any number will come out to be a positive, right? So this is 9 times some positive number right here. Well, I know that 9 times a positive number is positive, right? And so therefore, this number, whatever it comes out to be, is greater than 0. All right? So this is a true statement. That means that 0 is a solution, right, to this inequality. Not only that, because it's all or nothing on each piece, that means every number to the right of negative 9/2 is a solution to this inequality. All right, that means that whenever I take any number on this piece and I plug it into the derivative, it will be positive because it means that it's greater than 0, right? It has to be if it's a solution. All right, so that's really the important part, is that when I take any number in this piece right here, plug it into the derivative, I will get a positive number out. So what I do is I go back here and I rewrite this as a plus. I don't really care about the test number. Right, all I really care about is, did I get a positive or a negative number when I plug it into the derivative? So I mark that interval with the big plus. And I'll know that the original function then will be increasing on that interval. All right, same thing with the negative 5. Let's plug that in. I'm going to erase this part right here. And we're going to plug in a negative 5. So I get 2 times negative 5 plus 9 e to the 2 times negative 5 minus 1 greater than 0. Okay. And so I get over here negative 10 plus 9 e to the negative 10 minus 1. So I get negative e to the minus 11th greater than 0. Okay. So again, if you have a calculator, you can just plug this in here and see what you get. I'm not going to do that, right? I know that I have a negative sign here, and then e to the negative 11th is a positive number. I know that, right? Because e to any number is positive, right? And so I have a negative times a positive, that will come out to be a negative, okay? So what that means is that for this interval over here to the left, I get a minus on that interval, okay? So I have my sign diagram completed on here. And once you have that sign diagram completed for the derivative, then you can just look at it and write down the answer, the intervals on which f is increasing and the intervals on which f is decreasing. Okay? All right, so the original function f is going to be increasing on the interval from negative 9/2 to infinity, wherever there's a plus, right? Which is right here. All right, and then for decreasing, it's going to be those intervals where there is a negative. So that would be this interval from negative infinity to negative 9 halves, like so. Okay. Okay, and that's it. Now, just the standard warning if you watch the other videos is, your teacher might want you to put a bracket on here, or the book that you're working on might give the answers in terms of the brackets right here. And I've seen that vary from book to book. So in my class, I usually don't worry about it that much. And on the quizzes in my class, this is kind of how the answers will appear. All right, that's it for this one.